So hello everyone. So in this video I'll discuss the ideal differentiator circuit with the practical op-amp. So when I have discussed the ideal differentiator, so the op-amp I have considered as ideal, right? So when the op-amp was ideal, so we have got the transfer function as of this ideal differentiator as minus RCS, right? This was the transfer function, but now this op-amp is practical, is this AOL is having a finite value. So now this virtual one concept is not valid here, means this inverting terminal voltage is not equal to 0 volt. So we have to go with the basic output voltage of op-amp, which is AOL into VD. This is the difference voltage, non-inverting minus of inverting. So V naught is equals to AOL, and this is minus of V inverting. So V inverting is minus V naught upon AOL, right? So now we will apply again a KCL at this inverting terminal. So this is the impedance 1 upon CS. When we apply KCL, we will again finding the generalized expression for this transfer function when this op-amp is practical. So this is the V in minus of V inverting, and upon 1 upon CS is equals to V inverting minus of V naught divided by R, right? So this will be this R we can shift here, so this will be RCS into VIN and minus RCS and V inverting, that is equals to V inverting minus of V naught. So now this is the RCS VN and this is V inverting and 1 plus of RCS and minus of V naught. So simply substituting V inverting as minus V naught upon UL, and this will be 1 plus RCS and this will be minus of V naught, and this is the RCS VI. So if I take this V naught common, so it will be, or minus V naught common, so it will be 1 plus RCS upon AOL and plus 1, right? Now taking the LCM, so it will be RCS and VN, this is minus V naught and this will be AOL, and this is 1 plus RCS plus AOL, right? And we have to figure out this V naught upon VN, it will be minus RCS into AOL, right? And upon 1 plus AOL plus RCS. Now this is the transformation that we have got, right? So from here we can see there's a 0 at the origin and the pole. So 0 is at the origin and pole is at minus 1 upon, this is the minus 1 plus of AOL and upon RC, right? This is the pole location. So if we draw the pole 0 plot, this is interesting that this is the 0 at the origin and pole is at minus 1 plus AOL and upon RC, right? So this is the first order high pass filter, right? On the first order high pass filter pole 0 plot, and from here the time constant is RC upon 1 plus AOL. So this is the generalized result of the time constant of differentiator circuit, which is RC upon 1 plus AOL. This is the generalized result. And from here we can see that if this AOL is infinite, means the op-amp is ideal, so the time constant will be 0 second, right? So we can say it does not exist because it is not having a finite value, and I have a mistaken here in the ideal differentiator which I have discussed here. This is the ideal differentiator, and I have said that the time constant is not defined, so this is not good. Not defined is not a good terminology. This should be time constant not exist or actual value it is 0 second. So this is my mistake, so sorry for that. This is 0 second, we can see from this generalized expression, right? So this is the first order high pass filter. We can see from here also, right? And it is at zero frequency, the magnitude will be zero, so it means the low frequency is not passing, and at infinite frequency the order of numerator and denominator are same, so simply it will be AOL, right? Coefficients will be divided, so simply AOL. So high frequency is passing, so it is a high pass filter. So as the practical differentiator behaves as a low high pass filters, same if we want the high pass filter from ideal differentiator, the op-amp should be the practical. So ideal differentiator can also act as a high pass filter with the practical op-amp or the finite here. Open loop gain should be finite. So this is a good concept, and this result is not necessary that is RC upon 1 plus AL or this one, because there can be confusion if we remember this result RC upon 1 plus AL, because in the uh, ideal integrator with the practical op-amp the result was RC into this RC into 1 plus AL, right? So that's why this result is not important. This basic form is very much clear in always. Whenever this AOL is finite, we have to go with this form, and we have to perform this to be practiced or performing this if this is the if the op-amp is practical given. There's no need to remember these results and all, right? So this is the good concept of ideal differentiator with the practical op-amp. So okay, thank you.